Hello, everyone. Today we are going to continue on with our Chapter 18 homework. So we will go ahead and do that. So we left off on problem 18. So we'll go to question 19. So question 19 says, consider each set of substrates and select the substrate that would react more rapidly in a nucleophilic aromatic substitution reaction with either CH3O or CH3OH. So let's think about that. And we are going to select, let me see. So we have parts A and B. We're going to select option 1 here, and then we're going to select option 2 here. So in the first one, we're going to select the tri-substituted compound. So that's going to react faster than the disubstituted compound because the anionic intermediate Mesenheimer complex is stabilized by both substituents rather than just one. So that's why we're going to pick option 1. And option 2, we're going to select the para-substituted compound. Since that reacts more rapidly than the meta-substituted compound, since p-nitro group contributes an additional resonance structure to stabilize the electron pair of the Mesenheimer complex. So that's what we're going to select. So the first one, this is a tri-substituted. And here we're selecting the para. It all has to do with the stability of the Mesenheimer complex. All right, so that's 19. We'll go on to 20. 20 says 2 major organic products are formed in the reaction of perchlorotoluene with sodium amide. Draw the structure of both products. So let me see. So here we're going to have a benzyne. So, okay, so we have this right here. Oh, let's draw that better. Remember, chlorine's a really good leaving group. We still have that proton here. And this amide is a good base. It's going to do this. It's going to be gone. Then we're going to have something like this, where I have this benzyne group, right? then this group can either come in here or come in here. It can come in either place. So depending on where that attack is occurring, and if it obviously comes in here, then there'd be a lone, there'd be a lone, this would come here, this would generate a lone pair of electrons, and then it could take that, we just generate NH3, right? So it can take a proton here, and that's how it can get reprotonated. So we have two products. And these are your two products. That's question 20. So let's go to 21 then. Twenty-one says devise a three-step synthesis of 2,4,6-tribromoaniline from benzene. So R1, first we're going to put a nitro group on here. So to put a nitro group on, you put NH3, H2SO4. And then to get that to become an amino group, if we want this to become an amino group, we just have to add R2, which means it's zinc, mercury with HCl, HO minus. So then we have an ortho directing group on here. So all we have to do now is add our reagent 3, which is going to be bromine. So this will take this to the nitro group, right? I'm just going to draw it like this. Then this is going to be converted to an NH2 group. And then we're going to have a ortho director now. And I'll place those bromines ortho to the NH2. So we get our final products. It's an ortho para director, so we will get some in the para direction too. So we have bromines in the ortho direction and in the para due to the NH2 group. So that will solve 21. All right, so let's go on to question 22. It says draw the structure of the major product of each step in the given three-step synthesis. Show the formal charges where applicable. So we have an alkyl substituent on this benzoic group. And this will be converted into a carboxyl group with sodium chromate. It's a good oxidizing agent, so we'll draw product 1. That's P1. Now we have a meta director here. This is going to be a meta director, so you can only imagine where we're going to put the nitro group on then. And we'll get rid of this. I mean, I'll put it right here that way people don't get confused of what to put for the answer. Well, let's draw that a little down. That way we're not going to run out of room here. We got our carboxylic acid. We have our meta director. So it doesn't matter what side you put this on. And it wants formal charge here. So put a minus here and put a plus here. So once we have that, we're going to add the bromine. So let me see. So we have a meta director here. We have a meta director here. So there's only one spot to put this in the meta position. So it'd be here, right? We're going to be going here. So again, let's not confuse anyone with this. This is where we're going to meta direction because they're both meta directors. So P3 is just going to put the bromine at that position. So we'll draw P3 right down here. We got that bromine there. We have everything else. That's it. So those are your 3 products. All right, so hopefully that gave you enough time to put all three answers in. So we'll go to 23 then. '23 says this is a 4-step synthesis. All right. So we start with this. I'm going to make my life easy. I'm just going to draw the abbreviation for the benzene group. This is my abbreviation for it, just making my life easy here. So we're going to add an alkyl group to this, right? So to add an alkyl group to it, then we're going to have this group coming off. Now we're going to add NBS to it. Now we added that bromine to it. So let's go ahead and add bromine. And the bromine here. Oh, I'm getting close to the top, so it's becoming more difficult. So we got that. And that's a radical bromination right there. So first we did the Friedel-Crafts, then we did our radical bromination. Now let's add a strong bulky base. So we're going to get rid of this bromine here with a strong bulky base. And what strong bulky base do you think we're going to use? Tert-butyl oxide. So we have this CH3. And this base is going to come in here, take that proton, and it's going to go, right? So if we do that, then we're going to have this right here. Now, how are we going to form a ring? We have to think back to a previous chapter for an epoxidation. We're going to use meta-chloroperioxybenzoic acid forming 2-phenyl-oxyrane. So MCPBA. That's from a previous chapter. When we do that, we're going to form our epoxide. So that's it. So that's our 4-step synthesis. Friedel-Crafts, radical bromination. Then we have a strong base, our tert-butoxide. Then we're going to use our MCPBA to make the epoxide. All right, so let's go on to 24. So 24 says in each reaction box, select the best reagent conditions. We have another 4-step reaction here going on. So again, I'm going to do my abbreviation. We're going to start with our benzene, right? Then we're going to go through a Friedel-Crafts alkylation. So let's go ahead and put our Friedel-Crafts alkylation in here. So now we have our methyl group sticking off, right? Then we're going to do our radical bromination again. So here we have a radical bromination. And then what we're going to do is we're going to have an SN2. So we're going to go with an SN2 reaction. So, substitution, nucleophilic, bimolecular. So it's a concerted reaction, right? So we're going to add NaOH to it. We get NaOH to it, concerted reaction, we're just replacing that bromine. Bromine's a good leaving group. And then to convert it to the aldehyde, we got to think back to a previous chapter. We're going to use PCC. All right, so hopefully you had enough time to answer that question. Let's go on to question 25, the final question of the chapter 18 homework. Again, this is going to be a multi-step synthesis, combining everything what we've learned. Here, this one's a little more involved. So we have this. I'm going to try to draw this as close to as I can. And we have the OH group here, right? So what we're going to do to put it on the other side, we're just going to add Br2. So we have Br2. Now we're going to OH. It's going to be orthometa-para. So this bromine is going to be in the para position. I'm going to put a little P here so that you know that. Then we're going to be thinking about here for reagent 2. Let me think. So we're going to have to form an alkoxide for with reagent 2. So well, how we're going to do this, we're going to have sodium hydride. Oh, it's not writing. Oh, my pen's not writing. Let me see. There we go. I have sodium hydride with alkyl bromide, so methyl bromide. Again, this is in the para position. I'm just going to indicate that with a P. Now, when you add so I'll draw this out when we have to draw it out. When we add the magnesium in the ether, now we're kind of creating our Grignard reagent. So let's come down here. We'll draw this one out since they want it to be drawn out. Let's draw that a little better. We'll get rid of that line there. So we'll just come up here. That way we're not confused. Doesn't matter. We have 2 electrons. I don't know if they need that. And then in the para position, we have our magnesium, and then we have our bromine. I don't know how particular they are with angles, so they may be a little particular. So identify reagent 4. So reagent 4 is a nucleophilic addition of the aryl Grignard reagent to the electrophilic carbonyl carbon of the acetone, forming a tertiary benzoic alcohol. This pronation of the alkoxide formed from the Grignard reaction would occur during acidic workup. So that's what we'll provide then. So reagent 4, R4. You can only imagine, if we had acetone, that, here we have this, it's going to come in here, it's going to release. We have a dehydration reaction, so we're going to get rid of that oxygen too. So to do that dehydration reaction, let me see what we're using. We're using H2SO4. And I'll get rid of that water, because if you have, let's just say, let's just say you had an oxygen here and you had this. Well, we're going to add another hydrogen there from the H2SO4. We're going to get rid of it. It'll be a good leaving group. It's called dehydration because we're getting rid of water. And now we have to just draw the product. So our final product will be something like this. So I'm going to give everyone a few minutes there to make sure. I don't know why I put question 18. This should be question 25. So that's question 25. So we have the bromination followed by, and the sodium hydride with their methylbromine to form our alkoxide. Then we are going to form our Grignard reagent with our magnesium ether. We have to draw out this structure, right? That's why I drew it out. And then we're going to use R4. That's going to be the product for R4. And this is your dehydration right here, right? So, I don't think you have to put this because they put this in for you, but you're going to use H2SO4 for the dehydration to get rid of the alcohol right here. So that's everything. So I'm just going to leave this up there so you can input the answer, and then we will take a break. Well, I'll ask if anyone has any questions, and we'll take a break, and then we'll go on to chapter 19. So take a few minutes, make sure you have it all, and just be patient. And we did this homework pretty good. It combined all our thoughts. I think we did really good. All right, everyone, I don't see any questions. So let's take a 15-minute break. We'll start with chapter 19. I'll load this up on Blackboard and we'll reconvene in 15 minutes. All right, hello everyone. Welcome back. Welcome to chapter 19, the study of aldehydes and ketones. And on the next slide, we're going to see exactly what is an aldehyde and a ketone. This should be a refresher, but we'll show you anyway. So an aldehyde has this R double bond with a carbonyl group, but here's the hydrogen. A ketone has two R groups. So they're important in biology and industry. The simplest aldehyde is used as a preservative. They often use this as a preservative for dead bodies. They put formaldehyde in there. So it's just this group right here with two hydrogens. And acetone is the simplest ketone. You can commonly find this in nail polish remover. There's a bunch of different aldehydes and ketones as products that we see, such as vanillin. That gives us our vanilla flavor. To extract out the vanillin from the vanilla bean, you have to use ethanol to extract this out. You have cinnamon aldehyde, carbone, which gives us our spearmint flavor. Benzaldehyde, which is an almond flavor. We can also find ketones. Here's your ketone groups, and testosterone and progesterone. So these are different places that you can find these different functional groups. So there are 4 discrete steps to naming an aldehyde or ketone. It's the same procedures as with alkanes or alcohols. Identify and name the parent chain, identify the name of the substituents, the side groups, assign a locant, a number to each substituent, and assemble the name alphabetically. All right, so hopefully I give you enough time to write down the steps. So you want to identify and name the parent chain. So for aldehydes, you're going to replace the E ending with Al. So butanol. We have this carbonyl group with the hydrogen. The parent chain must include the carbonyl carbon. So we are including so for instance, the parent must include this carbon. So 1, 2, 3, 4, 5, 6. So we have hexanol. So they give us some examples. The aldehyde carbon is assigned number 1. So it'd be incorrect to go the other way around. So for ketones, replace the E ending with ONE, so butane 1. So the parent chain must include the carbonyl group. The carbonyl group is given the lowest number and can be expressed before the parent name or before the suffix. So we have 3-heptane 1. So we have heps, which is a 7-chain alkyl group, 7-chain carbon group. At the 3 position, we have our ketone. So chiral centers, the configuration of chiral centers indicated at the beginning of the name. So here the chiral center is right here. So let me see one. So be going this way, we flip it because the hydrogen's coming out. So this would be the R position. Aldehyde next to a ring is named as carbaldehyde. So cyclohexane carbaldehyde. And that's because this is an aldehyde right next to a ring. So there are also some common names like formaldehyde, acetaldehyde, and benzaldehyde. And where did we see benzaldehyde? Well, we already saw it right back here for an almond flavor. So next time you find yourself, eating something that has an almond flavor, maybe they use some benzaldehyde. So I'll just leave that up there. I think that's kind of interesting. All right. So there are some different ways that they talk about of making these aldehydes or ketones, and they're referring you back into some previous chapters. So chapter 12 talks about how to do an oxidation of primary alcohols to form the aldehyde. Chapter 8, we're forming aldehydes from this reaction. Chapter 9, chapter 12 again. Remember, this is going to take this OH to the ketone. Chapter 8, just break this right here. Chapter 9, acid catalyzed hydration of terminal alkynes. Friedel-Crafts acylation, we just talked about that. So the carbonyl carbon is electrophilic, and this is derived from resonance effects and inductive effects. So you can see the resonance effects right here. So the carbonyl carbon is attacked by nucleophiles. So if you have a good nucleophile, you can attack that carbonyl right here. Remember, we just, the Grignard reagent in problem 25 from chapter 18, we had some type of Grignard, comes in here, you can do a nucleophilic attack. And then how did we get rid of this? Remember, this was here, and then we had dehydration reaction with H2SO4. And it does become so it becomes an sp2. The point here, though, is you're turning an sp2 carbon into an sp3. All right. So aldehydes are generally more reactive towards nucleophiles than ketones. There's sterics involved. So look at this. An aldehyde has less sterics right here. There's no R group. There's no second R group is what I should say. Electron effects. Aldehydes have a larger delta positive on the carbonyl carbon. So in the ketone, this has 2 electron donating alkyl groups that stabilize the partial charge. Here, there's only 1 electron donating alkyl group, right? So it's not going to be as stable, so it'll be more likely to undergo nucleophilic attack. So as a result, aldehydes are, they're more electrophilic. So they're more, that means they're going to want to take those electrons from that nucleophile, aren't they? So if we have a nucleophile, they're going to want to really eat that up. So some nucleophiles require acidic conditions, others require basic conditions. So example would be the Grignard reaction. It requires equals basic conditions. So generally a strong nucleophile means the reaction is under basic conditions. So the Grignard reagent itself provides for strongly basic conditions because Grignard reagents are both strong nucleophiles and strong bases. So this reaction cannot be achieved under acidic conditions. It says, please note that Grignard reagents are destroyed in the presence of an acid. So under basic conditions, all nucleophiles react with carbonyls by the same general mechanism. You can see that mechanism right here. We have a nucleophilic attack followed by a proton transfer. So nucleophile attacks forming a negatively charged intermediate. Well, here's your negatively charged intermediate right here, which is protonated upon acidic workup. So aldehydes and ketones react with a variety of weaker nucleophiles under acidic conditions by the same general mechanism. So here, this is under acidic conditions, right? There were proton transfer from the acid, followed by the nucleophilic attack. So the carbonyl is protonated to form a positively charged intermediate. So before we formed a negatively charged intermediate, but we're forming a positively charged because we have an acid in there. So acidic conditions are required in order for a weak nucleophile to attack a carbonyl group. Protonation of the carbonyl makes it a better electrophile. And that's because if you have this protonated, you have a full positive charge instead of just a partial positive versus a partial negative, right? What would be better? Well, this would be more powerful because it has a full formal positive charge right here. So then you go into this, when a nucleophile attacks the carbonyl group, the equilibrium depends on the ability of the nucleophile to function as a leaving group. So this is favored at equilibrium. So since the nucleophile chlorine is also a good leaving group, equilibrium favors the starting ketone. Well, that's because it's a good leaving group. We've talked about chlorine being a really good leaving group for a long time. So this chapter will cover the following nucleophiles and the reactions with ketones and aldehydes. Well, you give a bunch of different nucleophiles here. So So the first one we're going to look at is then the oxygen nucleophiles. So in the presence of water, a ketone or aldehyde is in equilibrium with its hydrate. You could just think about this as coming in here like this, coming in here. And then this is going to take a proton from water. So this is how we're going to get this hydrate. So the equilibrium generally does not favor the formation of the hydrate, except for very simple aldehydes. Well, what's the most simple one? Well, formaldehyde would be the most simple one. So the rate of reaction is slow unless acidic or basic conditions are used. And they go through and they show you the nucleophilic attack followed by the proton transfer. And this is how we're going to generate the hydrate over here. But what if, what if we could put a proton here and we could force this into being a positive charge? Well, we might make the reaction go much quicker then, right? So this is the whole idea behind the acid catalyst catalyzed reaction right here. So we're gonna have a proton transfer. We generate a full positive charge. Then we come in with a nucleophilic attack, proton transfer. So the oxonium intermediate is deprotonated by water to form the hydrate. So this is your oxonium intermediate right here. And then they make this really important note in the text. They say, under acidic conditions, a mechanism will only be reasonable if it avoids the use of or formation of strong bases. So a strong base cannot exist in an acidic environment. It'll be neutralized. Under basic conditions, a mechanism will only be reasonable if it avoids the use of a formation of strong acids. And a strong acid cannot exist in a basic environment, again, because it'll be neutralized. So alcohols can attack ketones and aldehydes where they form this acetyl group. Here's your acetyl group. So this would come in like this. We have your nucleophilic attack, followed by a proton transfer, followed by a second proton transfer, and then we have a loss of a leaving group, a nucleophilic attack, and then a proton transfer, but we'll see that on a slide. So under acidic conditions, one ketone aldehyde reacts with two alcohols to form an acetyl. This is how we do it. And it's a few steps that go through this to form this acetyl. Like I said, we're going to see that on another slide. So commonly used acid catalysts for acetyl formation include para-toluene sulfonic acid and sulfuric acid. Like I said, here's the mechanism how to form the acetyl. You have a proton transfer followed by a nucleophilic attack. Proton transfer make this a positive charge, right? And then we'll have another proton transfer. Now we have our hemiacetyl. Well, we call it a hemiacetyl because we only have one acetyl group. So then we have another proton transfer, loss of a leaving group, because water is an excellent leaving group. Then we have another nucleophilic attack, followed by a proton transfer, and we have our acetyl. So the formation of the hemiacetyl involved 3 steps, right? 1, 2, and 3. And note that the beginning and the ending both involve a proton transfer. And this is some type of weak base right here. So we come to this position, let me see. Right here, this is not an SN2 reaction right here. SN2, cross that out. This is not an SN2 reaction because there's sterics in here. Otherwise, this would all happen at once. And this is not all happen at once, is it? We have a nucleophilic attack followed by a proton transfer. So acetyl formation is an equilibrating process. For most simple aldehydes, the acetyl is favored at equilibrium. So, formaldehyde is the most simple aldehyde that there is. And we can see that, the acetyl formation is the favored product. They have this arrow is longer. It's indicating it's more favored. For most ketones, the acetyl is not favored at equilibrium. So they're drawn at the other direction. So the reactions are favored at equilibrium. So forming all this stuff is a 7-step process. So if a diol is used, let me see. If a diol is used and both equivalents of the alcohol come from the same compound. So here's our diol. There's 3 steps and then 4 steps. So this is 7 steps. So once we do this, let me see. So eventually, it takes 3 steps to form the hemiacetyl, 4 steps, and they do this because this is a protecting group. So acetyl formation, let me see. Acetyl formation is reversible and can be controlled by adding or removing water. So if we add water, we go in the reverse direction. If we remove water, we go towards the acetyl formation. So to do this reaction, they're saying use a protecting group for the ketone. So first, you're going to protect the ketone. Remember, we talked about how to go back. If we just add water, we're going to generate our ketone back. So we can protect our ketone now. So then we can reduce the ester and deprotonate the ketone overall. So lithium aluminum hydride, this is going to reduce the ester. And then we're going to add H3O plus. And that's if you want to protect your ketone. So let's just say we did not protect the ketone, we'd also reduce this group too, right? If we're going to just use, let's just say we're not going to do this, and we're just going to do this. Well, we're going to reduce this group too. We're not looking to reduce that, That's why you have to protect it for it. So a hemiacetyl is the intermediate form of the conversion of a ketone aldehyde to an acetyl. They are generally difficult to isolate as equilibrium either favors the aldehyde ketone or the acetyl. So these are really hard to isolate. However, cyclic hemiacetyls can usually be isolated. So a cyclic hemiacetyl is possible when a compound contains both the carbonyl group and the hydroxy group. This is a cyclic hemiacetyl. And cyclic hemiacetyls are important in carbohydrate chemistry. And this is favored, they're both favored at equilibrium. And I think that's a good spot to leave on. I don't want to start 19.6, so we'll leave off there. We'll start 19.6 tomorrow, our next lecture. So have a great day, and I will see everyone next lecture.